Organic Chemistry, Chem 212, Exam 2 material, Part 1. We're going to look at Stereochemistry of Alkanes and Cycloalkanes. Taking a look at the shapes of molecules. Stereochemistry is concerned with the three-dimensional shapes of molecules resulting from many forces. Conformations are different arrangements of atoms that result from the rotation around a single bond. Below we have a picture of ethane and free rotation around a carbon-carbon single bond. So this illustration shows a rotation around the carbon-carbon single bond. Conformers is a specific conformation. It can't be isolated because they move too rapidly. Conformers interconvert rapidly, and a structure is an average of the conformers. Representing conformations. Go ahead and build the model of ethane so you can go ahead and follow along with these illustrations. Sawhorse representations show molecules at an angle. The carbon-carbon bonds are at an angle to the edge of the page, and all carbon-hydrogen bonds are shown. In the Newman projection, we look at how the carbon-carbon would look like if we had it end-to-end on paper. Bonds to front of carbon are lines going to the center, while bonds to the rear carbon are lines coming out of the edge of the circle. Looking at ethane's conformations. The most stable conformation of ethane has all 6 carbon-hydrogen bonds away from each other. This is known as the staggered position. The least stable conformation has all 6 carbon-hydrogen bonds as close as possible. This is the eclipsed. In a Newman projection, we can see that pretty easily. Now this energy is due to torsional strain. We can see on the graph here that there's energy involved in this. We have 12 kilojoules per mole. This is a value you do need to know for this class. I urge you to go ahead and take your model of ethane and rotate it so you can see the difference between the staggered and eclipsed. Conformations of propane. Go ahead and build the model from your ethane. Just add another carbon to it, another CH3. And we can see that we have a torsional barrier around the carbon-carbon bonds that costs 14 kilojoules per mole. When we have the staggered conformation, this form here, we can see that everything is away from each other as far as possible. But when we look at the Newman projection of the eclipsed, these two hydrogens, let's look at the bottom here, these two hydrogens here cost 4.0 kilojoules per mole. On the left-hand side, we have another 2 hydrogens interacting with each other. That costs an additional 4 kilojoules per mole. And then we have a CH3 interacting with a hydrogen, and that costs 6 kilojoules per mole, for a total of 14 kilojoules per mole. On the previous slide, we only had the hydrogen-hydrogen interactions on the eclipsed, and we had 3 of them, and that's why it was 12 kilojoules per mole. Conformations of butane. Add another carbon to your model. The anti-conformation has 2 methyl groups 180 degrees away from each other. Let's take a look at this graphic here. This is the anti-conformation. So take your model and you're going to sight along carbon 2 and 3, have those eye level to you, and the CH3 going up that's closest to you, and the one behind you is going down. And these 2 CH3s should be in the same line as each other. Now again, one's in the front and one's in the back, but these should be in the same line. This is the anti-conformation. This is the lowest energy. The highest energy would be the eclipsed form when both CH3s, for example, are on top. If we're taking a look at the graph of energies, the eclipsed, where we have the CH3s next to each other, costs 19 kilojoules per mole. Whereas we have the anti-conformation, that's 0, because that's the most stable conformation we have. So take your model and make these different conformations, take a look at the interactions that are happening, and you do need to note the energy cost for each of these, keeping in mind anti is the baseline at 0, and the worst, well, that's when we have the eclipsed with both methyl groups on the same side. We have staggered conformation with methyl groups 80 degrees apart. This is known as gauche conformation. And gauche conformation is the second lowest. What happens is, if we take a look at this graph, and let's put an imaginary line through the middle right here. Do you see where I'm putting a line right through here? I want you to notice that the lowest energy levels every time are any time we have the staggered in the anti or the gauche position. The highest energy levels, regardless of where the methyl groups are, is when we always have the eclipsed. The most stable conformation of any alkane is the carbon-carbon bond staggered, with the large substituents anti to one another. Taking a look at cycloalkanes, this is known as the Baeyer strain theory. In 1885, Baeyer looked at the different bond angles, and this is what he came up with. Since carbons prefer to have a bond angle of approximately 109, ring sizes other than 5 and 6 may be too strained to exist. Let's take a look at cyclopropane. A cyclopropane, the bond angles are 60 degrees, and that's 49 degrees away from our preferred tetrahedral of 109 degrees. So this is what we talk about with strain theory, and we talk about the energy involved in strain. The angle is not close to the 109.5. We have a similar situation with butane. We have 90 degrees, and that's 19 degrees off. So that's still a little bit off of our preferred 109.5. So cyclopropane rarely exists naturally in nature because of this angle strain. And cyclobutane also rarely exists because of the 90 degrees. Now, when we get to 5-membered rings, it's actually just 1 degree off. And we're going to see once we get 5-membered rings, it's more stable than we think because now the molecule has a little bit of bending within the ring itself. And we'll see that in the next couple slides. Rings from 3 to 30 carbons do exist, but they're strained due to the bond bending distortions and steric interactions. We see that 3 and 4-membered rings are extremely high in strain energy, so they don't exist as much. When we have 5, 6, and 7-membered rings, it definitely lowers. In fact, 6 is a baseline. We don't even have any angle strain there. And then we can see as we increase the number of carbons, it goes up a little, but then again it goes down a little because again it can start bending. The ring itself can bend within itself, relieving the strain. So when we look at a molecule, what kind of ring strain are we looking at? We're looking at 3 different things. We have angle strain, torsional strain, and steric strain. Rings larger than 3 atoms aren't flat and assume a non-planar conformation to minimize angle strain and torsional strain by ring puckering. Larger rings may have more possible conformations than smaller rings and are more difficult to analyze. Angle strain, it comes from the expansion or compression of bond angles away from the most stable. Torsional strain, this is the eclipsing of bonds on neighboring atoms. Steric strain, repulsive interactions between non-bonded atoms in close proximity. So angle strain is the difference in bond angles. Torsional strain is the molecule eclipsed, or is it staggered? And steric strain, is there something in the way? Taking a look at our first cycloalkane, cyclopropane. It's a 3-membered ring, and it's planar because there's just 3 atoms. It's symmetrical with bond angles of 60 degrees. This requires that the sp3 base bonds are bent, and they're going to be weakened. Additionally, what causes a lot of strain on this is all CH bonds are eclipsed. This drawing we have right here, the Newman projection of a cyclopropane. This is fair game on an exam, so be sure to practice writing the Newman projection of a cyclopropane. Conformations of cyclobutane. Cyclobutane has less angle strain than cyclopropane, but more torsional strain because of its larger number of ring hydrogens. Cyclobutane is slightly bent out of the plane. 1 carbon is about 25 degrees above the plane. The bend increases the angle strain, but decreases the torsional strain until a minimum energy balance is achieved. Looking at the Newman projection of cyclobutane, and it is possible that you might be asked to draw the Newman projection of cyclobutane also. So let's take a closer look at that. What we're looking at here is these 2 hydrogens are not quite eclipsed. This is due to this coming out of the plane slightly. So it's going to reduce this torsional strain a little bit. This thick line here is showing us that it's coming out towards us, and because this wedge line is going away from us, that's behind it. Cyclopentane. Well, this is the first cyclomolecule that your model kit can handle. So I highly recommend making a cyclopentane with your model kit. The only tip that I can really give you is the bond lengths between all the carbons. You should use the same bond length between all 5 carbons, and then it seems to fit together a little bit better. Planar cyclopentane would have no angle strain, but very high torsional strain. The actual conformations of cyclopentane are non-planar, reducing torsional strain. 4 carbon atoms are in a plane. The 5th carbon atom is either above or below the plane and kind of looks like an envelope. So here we have the Newman projection of a cyclopentane. Be sure to learn how to draw that one also. Conformations of cyclohexane. Substituted cyclohexanes occur widely in nature. The cyclohexane ring is free of angle strain and torsional strain. The conformation has alternating atoms in a common plane and tetrahedral angles between all carbons. When we have it in this conformation, this is known as the chair conformation. Go ahead and take your model and make a cyclohexane and go ahead and replicate this where you have a carbon going up, a carbon going down, and you can see the zigzag. This is the Newman projection of cyclohexane. You should spend some time checking out the model and making sure that you are able to draw not only the Newman projection of the chair of cyclohexane, but also the chair conformation. This is the classic chair conformation. In fact, it comes from looking like a lounge chair where you would put your back here, your bottom here, and your feet would come down here. How to draw cyclohexane. The chair version of cyclohexane is probably the #1 things asked on every organic chemistry test I've ever seen. Be sure to take a look at this to get some help on how to draw it. Here's a link to the video that I talked about. Now, in this video that you're currently watching, you won't be able to see the video, but if you take a look at the instructor PowerPoints, you'll be able to click the link and also watch the video. I have more information about cyclohexane and its different conformations on the next slides. In the chair conformation of cyclohexane, we have what's known as axial and equatorial bonds. Axial bonds would be the bonds coming straight up from the top carbon here. Do you see the one in red? This is axial. It's coming straight up. Again, this is much easier to understand if you have the model with this. Then if we go around this clockwise, let's come down this way, you could see that the next axial is going down, and then following the bond line over, the next axial is up, the next one is down. In fact, what happens with all the axial hydrogens, or all the axial positions, is they alternate up, the next one's down, the next one's up, the next one's down, all the way around the ring. Each cyclohexane has 6 axial hydrogens, 3 above the plane of the molecule and 3 below. And in this picture, they're shown in red. You can see down here in the space filling model, also the axial ones. I went ahead and tipped this over and you can see the 3 on one side of the plane here. The equatorial hydrogens are those going around. Now remember, this is a tetrahedral, so you have a 109.5 degree bond angle, but they're the ones going around. And I want you to notice something about those also. They alternate up and down. Now, if you take a look at this hydrogen going straight up, which is my axial, the equatorial, it's 109.5 degrees, so it's going to come out lower than the plane of the atoms. And the next equatorial will be just above the plane, and the next one lower, and again they alternate going all the way around. When you draw the chair conformation, make sure that your hydrogens that are axial go straight up and straight down. You need to be deliberate on that. When you draw in the equatorial, don't forget the bond angle is 109.5, so don't make it 90 degrees and don't make it 180. Make it look like closer to 109. And I'm going to be asking you to clearly label them. Hydrogen that's axials, put A parentheses either next to the hydrogen or the bond itself. Equatorial, put E in parentheses either again next to the hydrogen or the bond itself. On the next slide, I'll give you more tips on drawing in those axial and equatorial hydrogens. Axial bonds, parallel up and down. but they also alternate. Equatorial, there are 6 equatorial bonds, 1 on each carbon. Now a cyclohexane, when it's in the chair conformation, isn't going to be stagnant. It is going to move. So we can look at the conformational mobility of cyclohexane. Chair conformations readily interconvert, resulting in the exchange of axial and equatorial positions by a ring flip. What we see in this first version are the equatorials are in blue and the axials are in red. And the ring is going to flip. Again, take your model and flip it, and you'll see what happens is they switch places. What was in the axial is now equatorial, and the equatorial is now axial. All right, see where it says ring flip? Take a look at these arrows. Do you notice that they're equal in distance? That means they're just as likely to be in the form on the left-hand side as the right-hand side. How to do the ring flip? It shows you right here. Go ahead and make your model and flip it and make sure you can see the other side. You're also going to be required to draw the cyclohexane in both versions, the pre-flip and the after flip. Practice drawing them. This is an energy diagram showing us what happens during the ring flip. When we start off with the chair, it's the lowest energy. And during this process, we get half a chair, and that's very high energy. We get close to the boat twist, and then we get the full boat. Now, I haven't shown you the boat yet, but I will on a slide very soon. And continuing on, we have this side coming down. We're in a twist boat, and we have a half chair, very high energy, and we're back down to the flipped chair. For this class, the conformations we're going to be most interested are the chair, the boat, and the flipped chair. On your cyclohexane ring, go ahead and remove 1 hydrogen and put a bromine on there. We're going to see the effect of ring flipping and what happens when a bromine is in axial position versus an equatorial in terms of energy. When bromocyclohexane ring flips, the bromine's position goes from equatorial to axial and so on. At room temperature, the ring flip is very fast, and the structure is seen as a weighted average. At the bottom of this illustration, you can see the axial bromocyclohexane. This would be an acceptable way to draw it if I ask you to draw this on exam. You don't have to show all the hydrogens. We have a ring flip going on, and now it's in the equatorial. Don't forget the cyclohexane in one form before the ring flip looks different. Remember, this carbon that has the bromine on it is going up. Now it's going down, and the bromine is in the equatorial position. Taking a look at the arrow underneath the ring flip, do you see how the arrow is longer in the direction for the equatorial and it's shorter in the reverse direction when it's in axial? That's because anytime we have one thing on a cyclohexane, one substituent, in this case bromine, anytime it's in the equatorial, that takes less energy than when it's in the axial. Conformations of monosubstituted cyclohexanes. The 2 conformers of a monosubstituted cyclohexane are not equal in energy, just like we talked about in the previous slide. In this slide, we're going to be looking at methyl cyclohexane. Here we have the chair conformation of cyclohexane with a methyl on it, and this methyl is in the axial position. Be sure to make this model again so this makes more sense to you. Well, what we have going on is we have an interaction of a CH3 with the other axial hydrogen, and then also the CH3 with another axial hydrogen. You might be able to see it in this model form a little bit better, or again your own model. This interaction costs energy for it to be next to each other. Remember, when we look at an atom, the atom has electrons in the outermost area, and electrons don't want to be next to each other. So atoms themselves don't want to be next to each other. That causes energy. And anytime something costs energy, they don't want to do that. They want to be energy free if possible. So we have our space filling model down here. We have the interaction here of hydrogen and methyl. So what is going to happen is a ring flip. The ring flip happens. Now my CH3 is on the axial position. And look at the difference. There's no interaction between this methyl with any other hydrogen. In fact, in general, equatorial positions give the more stable isomer. And again, in this ring flip arrow picture, we can see that the arrow written to the right, where the methyl groups is in the equatorial position, is longer. That means it would rather stay in that position, the lower energy position. And on the left-hand side, it's shorter. It takes more energy to be there. So we can make an analysis and figure out just how much does this cost. When we talk about the CH3 interacting with hydrogens, how much energy does this cost? In disubstituted cyclohexanes, the steric effects of both substituents must be taken into account in both conformations. So on this one, we're looking at disubstituted cyclohexanes, and we're looking at two CH3 groups on the ring. These two that we're looking at are 1,2-dimethyl cyclohexane. One of them is in the cis conformation, and the other one is in the trans. For this slide, let's take a look at the cis conformation first. We're going to look at it when our two methyl groups, and remember this is a 1,2-dimethyl, so they're on adjacent carbons, and they're cis to each other, meaning they're on the same side of the ring. When both of our CH3s are in the axial position, we would have one interaction with CH3 with a hydrogen on the top here in the axial position, and also another hydrogen over here. So they show this in blue here, two CH3 hydrogen diaxial interactions. So that would cost 7.6 kilojoules per mole. Well, if you wanted to know what one CH3 to hydrogen interaction is, you just take 7.6 and divide it by 2. We have two of them. We also have the situation that we have a gauche conformation. Remember the Newman projection where we saw gauche and anti? Well, we have a gauche happening, and that costs 3.8 kilojoules per mole. And I didn't mention here, but one of the CH3 is in the equatorial at this stage. The total strain is 11.4 kilojoules per mole. Now, if this undergoes a ring flip, the CH3 group that was axial is now equatorial. The one that was equatorial is now axial, and we'll see it's the exact same amount of energy. There's no difference. We still have one gauche interaction at 3.8 and two CH3 hydrogen diaxial interactions at 7.6 for a total of 11.4. You are required to know what energy cost there is for the gauche for each CH3H interaction and be able to calculate and analyze the total strain in any of these chair positions. On the ring flip, they have the arrows going in equal lengths in both directions. That tells us they're equal energy, just as likely to be in one conformation than the other. Taking a look at trans 1,2-dimethyl cyclohexane. So when you make your model, you need to go ahead and take one of your CH3s and put it on the other side of the ring. It's still a 1,2-dimethyl cyclohexane. Let's take a look at this. One trans conformation has both methyl groups equatorial and only a gauche butane interaction between the methyls. That's a cost of 3.8 kilojoules per mole, just the gauche. That's it. So take a look at this drawing here. Both of these are in the equatorial position. There's no other interaction. The total cost, 3.8 kilojoules per mole. In fact, so far, this is the lowest energy possible. The trans 1,2-dimethyl cyclohexane, when we have both methyls in the equatorial position, lowest energy so far. The ring-flipped conformation has both methyl groups axial with 4 1,3 diaxial interactions. Okay, let's see what that means. Taking your model, flipping it, and you're going to see that one of the methyl groups is axial above the plane, and the second methyl group is axial below the plane. That means that above the plane we have a CH3 hydrogen interaction and a second CH3 hydrogen interaction. We saw before that was 7.6. Also beneath it, we still have a CH3 hydrogen interaction and another CH3 hydrogen interaction, another 7.6. Add those together, that's 4 CH3 diaxial interactions. Now this one has no other interactions because it's anti to each other. But it's still 15.22 kilojoules per mole. This is our highest energy. So the trans 1,2-dimethyl cyclohexane, depending on which conformation you have, can be the lowest energy or the highest energy. The trans 1,2-dimethyl cyclohexane will exist almost exclusively in the di-equatorial conformation, and that's because it only costs 3.8 kilojoules per mole versus this 15.2. All right, compound chemistry. This is a piece of This Week in Chemistry, and I thought this one applied a bit. The most polar non-ionic compound synthesized is a cyclohexane ring with fluorine attached to each carbon. Each fluorine atom is pointing up, making the compound the most polar non-ionic compound known. It could have applications in liquid crystals. The boat conformation of cyclohexane. So go ahead and go back to the plain cyclohexane, removing everything else from it. We're now going to take your model and turn it into the boat and take a look at what kind of interactions happen. We have a steric strain of hydrogens at carbon 1 and 4. And if you take a look at the Newman projection, you can see there's also torsional strain that every one of these bonds is eclipsed. You will be responsible to be able to draw not only the chair conformation and the flipped chair, but also the boat conformation of cyclohexane and the Newman projections of both. Conformations of polycyclic molecules. Two or more rings, when they're fused together, that's known as a polycyclic molecule, and they have a common bond. Here we have trans-decalin, and this is two 6-membered rings where we have a common bond here. Well, both of these can be in the chair position, and this is in the trans when we have a hydrogen up above the ring and one below, or we can have the cis form of it where they're both on the same side, and it does make an interesting molecule in the chair position, doesn't it? Decalin consists of two cyclohexane rings joined to share 2 carbon atoms. The bridgehead carbons 1 and 6 have a common bond, so this would be 1, 2, 3, 4, 5, 6. So this is the bridgehead between carbon 1 and 6. That's the common bond. There are 2 isometric forms of decalin, transfused or cis-fused. Flips and rotations do not interconvert cis and trans.